In complexity theory, a decision problem is P-complete if it is in P and every problem in P can be reduced to it by an appropriate reduction. The notion of P-complete decision problems is useful in the analysis of which problems are difficult to parallelize effectively, which problems are difficult to solve in limited space. The specific type of reduction used varies and may affect the exact set of problems. If we use NC reductions, that is, reductions which can operate in polylogarithmic time on a parallel computer with a polynomial number of processors, then all P-complete problems lie outside NC and so cannot be effectively parallelized, under the unproven assumption that NCP. If we use the weaker log space reduction, this remains true. But additionally we learn that all P-complete problems lie outside L under the weaker unproven assumption that LP. In this latter case the set P-complete may be smaller. Motivation. The class P, typically taken to consist of all the tractable problems for a sequential computer, contains the class NC, which consists of those problems which can be efficiently solved on a parallel computer. This is because parallel computers can be simulated on a sequential machine. It is not known whether NC equals P. In other words, it is not known whether there are any tractable problems that are inherently sequential. Just as it is widely suspected that P does not equal NP, so it is widely suspected that NC does not equal P. Similarly, the class L contains all problems that can be solved by a sequential computer in logarithmic space. Such machines run in polynomial time because they can have a polynomial number of configurations. It is suspected that LP, that is, that some problems that can be solved in polynomial time also require more than logarithmic space. Similarly to the use of NP-complete problems to analyze the P equals NP question, the P-complete problems, viewed as the probably not parallelizable, or probably inherently sequential, problems, serves in a similar manner to study the NC equals P question. Finding an efficient way to parallelize the solution to some P-complete problem would show that NC equals P. It can also be thought of as the problems requiring superlogarithmic space. A log space solution to a P-complete problem would imply L equals P. The logic behind this is analogous to the logic that a polynomial time solution to an NP-complete problem would prove P equals NP. If we have a NC reduction from any problem in P to a problem A, and an NC solution for A, then NC equals P. Similarly, if we have a log space reduction from any problem in P to a problem A, and a log space solution for A, then L equals P. P-complete problems. The most basic P-complete problem is this. Given a Turing machine, an input for that machine, and a number t, does that machine halt on that input within the first t steps? It is clear that this problem is P-complete. If we can parallelize a general simulation of a sequential computer, then we will be able to parallelize any program that runs on that computer. If this problem is in NC, then so is every other problem in P. If the number of steps is written in binary, the problem is exptime complete. This problem illustrates a common trick in the theory of P-completeness. We aren't really interested in whether a problem can be solved quickly on a parallel machine. We're just interested in whether a parallel machine solves it much more quickly than a sequential machine. Therefore, we have to reword the problem so that the sequential version is in P. That is why this problem required t to be written in unary. If a number t is written as a binary number, then the obvious sequential algorithm can take time, 2n. On the other hand, if t is written as a unary number, then it only takes time n. By writing t in unary rather than binary, we have reduced the obvious sequential algorithm from exponential time to linear time. that puts the sequential problem in P. Then, it will be in NC if and only if it is parallelizable. Many other problems have been proved to be P-complete, and therefore are widely believed to be inherently sequential. These include the following problems, either as given, or in a decision problem form. Circuit value problem. Given a circuit, the inputs to the circuit, and one gate in the circuit, calculate the output of that gate. Restricted case of CVP, like CVP, except each gate has two inputs and two outputs. Every other layer is just AND gates, the rest are OR gates. The inputs of a gate come from the immediately preceding layer. Linear programming. Maximize a linear function subject to linear inequality constraints. Lexicographically, first depth first search ordering. Given the graph with fixed ordered adjacency lists, and nodes U and V, is vertex U visited before vertex V in a depth first search induced by the order of the adjacency lists. Context-free grammar membership. Given a context-free grammar and a string, can that string be generated by that grammar? Horn satisfiability. Given a set of horn clauses, is there a variable assignment which satisfies them? This is P's version of the Boolean satisfiability problem. Game of life. Given an initial configuration of Conway's game of life, a particular cell, and a time t, is that cell alive after t steps? LZW data compression. Given strings S and T, will compressing S with an LZ78 method add T to the dictionary? Type inference for partial types. Given an untyped term from the lambda calculus, determine whether this term has a partial type. In order to prove that a given problem in P is P-complete, one typically tries to reduce a known P-complete problem to the given one. In 1999, Jinyi Kai and D. Sivakumar, building on work by Ogihara, showed that if there exists a sparse language that is P-complete, then L equals P. Problems not known to be P-complete. Some NP problems are not known to be either NP-complete or NP. These problems are suspected to be difficult. Similarly, there are problems in P that are not known to be either P-complete or NC, but are thought to be difficult to parallelize. Examples include the decision problem forms of finding the greatest common divisor of two numbers, and determining what answer the extended Euclidean algorithm would return when given two numbers.